Oh, should be good. Don't fall over. Cool. All right. Let's see if I have. Yeah. Blank paper. All right. So let's do a couple just to make sure everybody remembers or learns right now. If you weren't here last time, how to read this chart. I got to really mark these buttons. There we go. Switches. So the chart. So a couple things. When am I allowed to use this chart? When you have a normal, isn't it crazy? The chart tells you when you're allowed to use it. When you have a normal distribution. What does the chart tell you? When you look up a z-score, it tells you what? The area below the z-score you looked up, right? Again, the chart tells you. When you look up a z-score, it'll tell you the area below that z-score you looked up. I like it. You guys are all like, I don't like answering questions. Stop it. That's my job. Shit. So let's do an example. So if I have a normal distribution and I want to know what area is, well, a few different ways. What area is below a z-score of negative 1.82? Or I could say, what's the probability that a z-score is below negative 1.82? So if I had a normally distributed test grade, what's the probability your z-score is less than negative 1.82? And that would be a bad place to be. All right? So then I look up on the chart, on the negative z-score side, that is insane, negative 1.8, and then the second decimal place is up here, negative 1.82. So there'd be just above a 3% chance. Right? So 0.0344, does everybody see that? So on the picture, where would I put that 0.0344? Yeah, it's great. Oh my God. Probably where we just said it would be. Right below that z-score we just looked at. So of course, if I look up a z-score of 0, what should I find? What does 0 do to the picture? Yeah, so if I look up 0 on the z-score chart, I should see 0.5. Half of the data is below that. And as I move up to the positive side, I'm going to keep adding more and more area below. That's why the answers on the chart keep getting, they're very small down here, because there's very little stuff way the hell out there. But as I move up and move up and move up, the numbers get bigger and bigger and bigger. That's amazing. Okay, I like it. Okay, cool. So let's try another more involved problem. Just to remind you guys, how do I find the probability that z is between 0.11 and 1.29? So try to draw that and then try to look up those two z-scores. Help each other out if you want. If somebody needs help near you. So whenever you draw this picture, you always put z-scores at the bottom, you put areas up above, because very often areas look like z-scores. Right, 0.34, is that an area or z-score? Could be either. I don't have a freaking clue. So you don't want to be mean to yourself. So what do you get when you look up 1.29? 0.90? 1.5? Okay. I'm with you. You were saying something the other day. And what about 0.11? 5438. Now, if you weren't here, hopefully you guys see how that z-score chart works, right? 0.11 is 0.11 right there. 0.1, 1. So that's why z-scores are going to be rounded to 2 places, because our chart only goes 2 places. We could use technology and get closer to the exact answer, but I don't care. I think you pick up things using this chart. You pick up how things are laid out. You pick things up instead of just push buttons. I have a method to my madness. Now, how do I get the area I want? This 0.905 is the area completely below that z-score. So that's way too much. So, of course, if I subtract this much, I'll be left with just this little bit that's in the middle. So you get 0.9015 minus 0.5438. What do you get?
0.3577.
Point who? 3577. So it's about almost 36% of the data would be between those two. I like it. Now, you probably are starting to wonder, maybe. Some of you guys, at least some of you guys are wondering, all right, this is great if I have a normal distribution. What if I don't? Well, that's why a big chunk of statistics is all about figuring out when will our distribution be normal enough. What do I check to see if the distribution is normal enough to use that chart? And there's also more normal distributions than we realize. Part of what we're going to talk about today is, well, every single problem we've done is about a single test grade or a single person. Pick one person, what's probably they have this. Pick one test, what's probably that has this. If you look back at that chart, that handout we did, pick one student at random. It's probably it took them this long to find a parking place. It's all about 1, 1, 1. But what's statistics all about? Really, is taking a sample, right? Don't just look at one person. I want to take like 50 people. What's probably that they took this long on average to find a spot. We're going to get into how do things change if I start looking at groups of things instead of one person at a time, right? That's going to be today.
What if the arrow is facing the other way?
Why are those arrows facing that way in the first place? Why did I face the arrows that way? Because the chart only gives me below the z-score I look up. I didn't choose that. It's the chart, the way the chart is set up. When I look up a z-score, the thing I see is the area below that z-score, always. I like it. Yes? Uniform. And that is a type of continuous distribution.
Okay. You had told us if its x is equal to exactly one part of that. I don't remember what you said.
And the funny thing is the same thing here. For any continuous distribution, I want you to realize this. How many z-scores are there on this chart? How many? Infinite number, right? Two. I don't mean marked. I mean total. There's an infinite number, right? So the probability of 1 out of the total, the bottom would be infinity. All right? That's kind of an oversimplification, but it's basically the idea. That's why any single z-score, it's probably z equals 0.11, 0. Why can't I use a chart for probably z equal 0.11? Because the chart only does less than, that's all it does. So the probability z equals something is 0. The same way for a uniform distribution. It probably takes exactly 14 minutes for that bus. I'll bet you anything it ain't exactly 14 minutes. It stops exactly 14. No, I bet you it's 14.0037. Because it's continuous. Oh shit, there's too many possible values for any specific value to actually show up. That's really weird. Don't think about it too much like I did when I first heard that. That's when I got my teacher to tell me about the idea of iota. Did I talk about iota a little bit? Iota is kind of like the inverse of infinity in a way. It's like what's infinity? It's a process. It's not a number, right? You just take, one way to do it is take 1, add 1, keep doing that. Right? That's infinity. Infinity just says go forever that way. So iota is kind of like get as close to 0 as you possibly can without touching 0. All right, that's enough of that. Basically, Jackie, I heard. Basically, it's the same for any continuous distribution, like a uniform, like a normal. The probability of something equaling a value exactly is 0, because there's an infinite number of values, so each one of them have to be 0. Okay. What about to do? All right. So what if I have this situation? What if I say the mean of some distribution is 419.3, and the standard deviation is 87.111, and I want to know the probability that, let's say this is some score on some standardized test, like the SAT, except it's something else. Let's say probably I wanted to probably somebody scores more than what you got, Jeff? Let's say scores more than 600 on this test. That's 419.3, 87.111 for the standard deviation. And I'll tell you, what's the one thing I haven't told you yet that actually allows you to actually do this problem all the way? Yes, so we'll say it's normally distributed. I have to be told it's normal, or I have to have a way of verifying that it's normal enough before I can use that z-score chart.
What do you mean?
Just what I said.
I mean,
Yeah, the z-score chart only works if I have a normal distribution. So either in the problems they have to tell me it's normal, or they have to give me a way to check to see if it's normal.
what happens if it's not normal?
Then we can't do anything. Not in stats 1 anyway. That would be a stats 2 problem.
How do you think it's normal?
Huh?
I don't know. Wait, how do you
Because I
think-
said so. But we haven't got later. So in chapter 7, we're going to hit our first way of telling if a given situation has a normal enough distribution. That's going to be part of what we talk about today. Right now, we just have to be told it's normal. We haven't learned any checks yet. I don't know. None of those questions had to be answered before you could do this problem. So everybody's looking at me. Draw the picture. We know it's normal. We know what the mean is. We know the point that we're interested in, and I know where to shade. If you missed last time, what is the thing that's going to connect this to the chart? What do I have to do in between? I have to make this into a z-score, because the chart's the z-score chart. Not the test on some weird-ass, the grade on some weird-ass test chart. So tell you it's normal, so you know the shape, so you know you're allowed to use the z-score chart. What goes right in the middle? No? The mean, which is?
41.
So why was I putting 0 up here? You're an asshole, Jeff, put 0, and then you don't put 0. Because these are all about z-scores. And what's always in the middle for z-scores? 0, because z-scores are how far away from the mean you are, and the mean is 0 away from itself. But here, this is an actual physical problem. I have a mean that's 419.8. Now, underneath it, I could put 0 as a z-score, sure. So I'm representing both the physical and the z-score idea. Now, where's 600? That's the point I'm interested in. Where is it? Yeah, it's above 419. So if I said 300, you better put it down here. Right? Because it would be below the mean. So 600 is somewhere up here. I don't have to know, and then I could figure out the z-score. And what's that z-score formula again? Yeah, x minus the mean divided by the standard deviation. I like it. How many standard deviations fit into that distance between the data point and the mean?
So what's the x?
What point are we interested in? What grade are we interested in? 600. That's the x. I've got to change that into a z-score.
So technically, we could like any number we're looking for and just plug it in.
Yeah, any grade that you have a question about, you can change it to a z-score. What are you guys getting for the z-score there? .07?
Sorry. He's rounding to 0.808 though.
It is? Okay. I like dissension amongst the stars. No, it's not? Ooh! It's even more interesting now. You guys notice I haven't put it in the calculator, so give me a second. I'm good at math, but I ain't good enough to do that in my head. At least not that precisely. Who's ready to throw down? I get 2.074, so it should be just 2.07. You got it?
Yes.
So 2.07. Now, real quick, up here on the picture, what area am I interested in? It's really just what side of 600. I want this side. Now, when I look up 2.07, it's going to give me the area below. So what do we get when we look up 2.07? 2.07. Yeah, 9808. So that's down here, 9808. Have I answered my question yet? No, I can see visually. I can see that. Nope, I haven't answered my question. See visually. I like that. Not with visually. And then what's over here then? 0192. I like that. Now, some of you guys, I talked to you about the shortcut. You can do a shortcut if you want to. What does this mean? What does this mean? Uh-oh. So this was all about picking one test and the grade being more than 600, right? That's the idea. So there's a couple different ways you can interpret that number, right? It's not just a number just floating around. It means something.
Why did I get a different pencil? Like when I
Oh, okay, fine. Your calculators understand order of operations? What are the order of operations? Please excuse my dumbass son. Or, yeah, you can take that if you want to. It's funny, and most people find it funny. Especially if you have a dumbass son, then it's really funny. Or like my math 90 students last semester, they said, please excuse my deficient algebra skills. Whatever works. Or deer on salad, if you want to go traditional or boring. Your calculator understands this shit. So if you put the z-score in, if you put this in as 600 minus 419.3 divided by 87.1, well, what's it going to do first? It's going to do the division first. You don't want it to do that. You want it to do this first. Oh, shit, I need parentheses to lift that sucker up to the first thing it does. So it sounds nice that your calculator understands order operations, but it's actually bad for you because that just means you better put that damn thing in right. Garbage in, garbage out. Okay, what was I saying? So what does this mean? Well, what's this question mean? What's this mean? What's this? The probability that a test score is higher than 600, right? So then this, one way to say it is very direct and very boring, is to say the probability is 1.92% chance that a test score is higher than 600. A slightly better way to say it is 1.92% of all test scores are above 600. That's a more real-life interpretation, right? So if I found the probability that somebody was taller than 70 inches, well, that is the percentage of all people that are taller than 70 inches. That's a more useful way to look at it. Okay, all right. So is everybody, how do you feel about using that z-score chart? Just how to use it. Is that all right? Yes? Cool? Yes. And then the next level is, if I give you X scores, you have to change them into Z scores. You ain't going to find 600 on that Z-score chart. Okay? All right, I like it. I like it. Okay, so let me give you this. Please, dear God, do not freak out about this side yet. We haven't talked about this yet. This is the side I want you to worry about right now. This is just some example problems using the z-score chart, cool, and the z-score formula.
Why are you confused about? No, it's because my calculator did. You're so much stupid. I get it. It's just. This is I'm just. The quiz we gotta study out. Like, no more cheesiness, no more lace. You were studying. When I was studying.